Okay, this is a simplified diagram of a small subset of what we know about how metabolism works, and it's bad enough, as you can see. But the real problem is, of course, that this is a simplified diagram of a small subset of what we know about how metabolism works, which is completely dwarfed by the utterly astronomical amount that we don't know. Even leaving aside all the probably even more astronomical amount that we don't even know that we don't know. So, you know, it's completely hopeless. There's no way in the world that we're going to be able to be cleverer than evolution and clean up this system in a manner that does not do more harm than good. It's just not going to happen. Now, there may be in your minds a little concern about what I just said, because some of you may have heard of some rather promising experiments that are occasionally reported, somewhat breathlessly in the mainstream media, with regard to the postponement of aging in model organisms, especially rodents. And I thought I would say a little bit about that. I'm going to call these things magic bullets, because essentially they are very simple interventions, typically single molecule pharmaceuticals or single gene interventions, that are able to affect pretty much all of the aspects of age-related decline, and which is, of course, a really, really complex, sophisticated outcome. And I want to explain why it would be premature, to say the least, to get too excited about that from a therapeutic point of view. The first reason is this. Whenever you've got a simple intervention, a simple thing that you do to an organism that has a very unsimple, very complex effect, you know that it must have been primed. There must be machinery in the body, in the organism's genetic machinery, that is sitting there waiting to respond to the intervention or to something like the intervention in order to respond in the appropriate way. In other words, there's got to be an evolutionary fitness advantage for that machinery to exist. And the particular magic bullet that we need to focus on here, because it really underlies pretty much everything you hear about that seems to succeed in postponing aging in model organisms, is calorie restriction. The phenomenon that was discovered in rats in the 1930s, whereby if you feed an organism considerably less, let's say 30% less than it would like to have, then it lives maybe 30% longer than it otherwise would. This is a remarkable phenomenon. It's very reproducible. It's been studied extraordinarily much over the past, 80 years now. We still have only a marginal idea about how it works, but the point is, it works because there's genetic machinery that we have that causes it to work. And unfortunately, if you think about the evolutionary logic of why that machinery should exist, it's pretty clear that longer-lived organisms will have less good machinery of that sort than shorter-lived organisms. The reason for that is the weather. Long famines are simply not so frequent as short famines. And very long famines, 20-year famines, are so infrequent that they simply do not provide enough evolutionary pressure to select against mutations that disable and eventually destroy the machinery that will allow the organism to respond to such a famine. It's the same deal as why you and I do not make our own vitamin C. Most of you probably know that most mammals do make their own vitamin C. But 3 times in the history of mammalian evolution, something went wrong. In apes, and in bats, and in guinea pigs, separately of course, a gene involved in the synthesis of vitamin C mutated itself into oblivion. And that happened because there was enough vitamin C in the diet all the time that when mutations happened in the germline, they were not selected against, and sure enough they took over, and by the time the vitamin C was available less reliably in the diet, it was too late. Same deal for machinery that responds to calorie restriction. Unfortunately, it's not just theory, it also seems to be true. If we look at the famous example of Okinawa, for example, this is an island at the south of Japan that has pretty much the same genetics as mainland Japan, pretty much the same composition of diet, but they have a culture that tells them to not eat so much. They just have this, I don't know, for whatever reason, they have a culture that says eat only in moderation. And they sure enough do eat considerably less than mainland Japanese. And they live longer. They do not live 20 years longer. They live like 2 years longer at most. And that, even though they spent all their lives eating less than your average Japanese. If those of us who have the misfortune to be already in this room, in other words, to have missed out on calorie restriction for some of our lives already, we will expect to get even less benefit. So it's not looking too good. But I just mentioned this is what I just mentioned, that you probably need an early onset intervention to get a real effect. And actually, it's probably not even linear. The benefit that you're probably going to see if you can really impose this magic bullet very early in life during growth is likely to be more, because growth is error-prone. Things go wrong then, rates of aging are more flexible then. This, however, is the real problem. We'd like to take people who are older than people in this room, people who are in a bad way, and fix them up. And if we are looking at these sorts of magic bullets, then we are implicitly capitulating on those people, and that's a bit of a shame. So I want to now move on to what the reason I'm here, because of course so far all I've told you is very pessimistic, and I wouldn't be here if that were the end of my story. 2 years ago, some of my colleagues tried to explain to the general public the problem with the gerontology approach, the complexity of metabolism and all that. And they tried to do it humorously. This is the front cover of Scientific American in which their essay came out. This was the title of the essay. And basically what they were trying to say was, you know, there are various ways in which the body could be designed differently so that it would last a bit longer. It would accumulate wear and tear more slowly. They decided that it would be good to have the knee articulated in the opposite direction, backwards rather than forwards. I think there was some argument about cartilage degeneration, I forget the details. And they had a lot of other similar things like that. Now, some journalists, including some journalists in Chicago, actually took them seriously and thought that this were a set of recommendations for therapeutic interventions in age. But of course, the real situation was they were just trying to make the point, albeit rather humorously, that, you know, hello, you're not built that way, therefore you're going to die, get over it. But the thing is that there's a little bit of a hole in that logic, and this is it. The human body is a machine, okay? Obviously, it's a very, very complicated machine, and unfortunately, we don't have the plans, but it's a machine, which means that there is a reasonable case for looking at simple machines for clues, for trying to figure out how to maintain the human body beyond what you might call its warranty period by looking at how we already successfully maintain simple man-made machines beyond their warranty period. And lo and behold, we do get some clues. This is a 50-year-old car. It's obviously, you know, that's pretty old for a car. Your average car lasts maybe 10 or 15 years before you junk it and get a new one. And the reason this car lasted much longer is because it was built that way, with corrosion-resistant metal and really tough tires and all those good things. And that's the same sort of reason why the human body lasts so much longer than a dog's body or a mouse's body. We've got better anti-aging machinery built into us. We are essentially more resilient against aging already. But the really important thing about this slide is not the picture. The really important thing is this up here. Why do you suppose I'm talking about VW bugs as the contrast? The answer is because there are just as many 50-year-old VW bugs driving around the streets of this country as there are 50-year-old Land Rovers. And the reason there are is not because they are built to last by any means. Rather, it's because they have another thing going for them. They've got style, which has caused their owners to fall in love with them and to do an exceptional amount of maintenance on them. This car works just as well as it did when it rolled off the production line, and that's why. It's because it's been well looked after. Now, what this tells us is that, at least for simple man-made machines, maintenance really works, just so long as it's comprehensive enough. If you only maintain your car as well as the law requires, then obviously it doesn't last 50 years. But if you maintain it considerably more comprehensively, then it does. And this leads us to at least the suggestion that we ought to consider the possibility of a maintenance approach to combating aging. This is what a maintenance approach turns out to be. Essentially, you don't want to intervene in this process whereby metabolism causes damage, and you don't want to intervene either in this process whereby damage translates into pathology. What you want to do instead is try and uncouple metabolism and pathology by diving in here and repairing periodically the various types of molecular and cellular damage so that they never get to the level that is pathogenic. And I'm pretty damned optimistic about this approach, as you can see down here. I think that this approach may have a chance of achieving a big extension of healthy human lifespan pretty soon. Why? Because it avoids the shortcomings of the other two approaches. First of all, it avoids the downward spiral problem of the geriatrics approach. So remember I was explaining that the problem with the geriatrics approach fundamentally is that it intervenes too late in the game, it's attacking the consequences of things that are accumulating, and therefore it's going to get harder all the time. The maintenance approach, by definition, targets the immediate byproducts of metabolism, side effects of metabolism, and therefore it does not have accumulating precursors. So that's a good start. But what's even more important is that the maintenance approach avoids the shortcoming of the gerontology approach. In this case, we are not asking us to clean up metabolism. We are not going to try to get metabolism to create these various types of damage at a slower rate than normal. We're going to let it do it at the natural rate. And then we're just going to go in afterwards and periodically fix that damage up. So in other words, what we're effectively doing here is sidestepping all of our ignorance about metabolism and allowing it to get on with doing what it's naturally doing, which means we don't need to understand it. We have a very good chance of being able to preempt its effects without actually messing with it. All right, so that's the irritatingly abstract theoretical part of the talk over. Now I'm going to talk some real biology. I've told you so far only one reason why the maintenance approach seems so promising, namely that it seems to target the weak link between being alive and being dead. But there's another one, which is this. If we look at actually what damage is in concrete terms, in molecular and cellular terms, it seems that it's a lot simpler.